So when you've done your flow material balance to get a lower estimate of your OIP, and you've also done your analytical RTA to get a lower estimate of your linear flow parameter or A root K, you're actually ready to do numerical RTA. So in the numerical RTA feature, just make sure that you have enough real estate to see all the plots on the screen. One thing that you can do in this feature is before you run the model is to exclude any data points here that you don't want to in terms of bottom hole pressures. Okay, and the way to do that is just to simply pick the lasso exclude right here. I'll just show that for example purposes now. So let's say I use the measured bottom hole pressures in this particular case instead, where there's much more noise. What I can go ahead and do is go in and exclude these data points right here. And what the software will then automatically do, if you're controlling this on bottom hole pressure, is to ignore those now gray points in the model, and it will actually just interpolate the points in between. But in this case, we're actually using this custom bottom hole pressure that we created earlier, and that's what we're going to use to then run our models. So the way you run it is just simply to click run, and what the software does is that it then spins up in this case, it spins up 5 different numerical models in parallel, all with just different pore volumes. And that's what we're going to use to create the basis for this analytical RTA or numerical RTA diagnostic plots. And in short, there are 6 diagnostic plots. And the key diagnostic plot is this Bowie diagnostic plot right here, the so-called numerical RTA diagnostic plot. And when I move this line right here up and down, you'll see that the linear flow parameter right here is also moving up and down and is changing dynamically. Okay, so this is exactly the same as changing the slope on the A root K plot. Okay, because the slope dictates what your LFP is. And here you see that my data is looking more or less flat, and then it starts to deviate for a period of time, and it lands in between these 2 type curves right here. So around 560 and then 930. But you also see that I'm pretty far off on my water cuts, and I also am over predicting my GORs a little bit. So before that, what I'd like to do is to change my rel perms a little bit. And at least if you would like to honor the water cut or the provided water saturation from the geologist in this example, the only way to produce more water would be to, or one of the most effective ones would be to reduce your connate water saturation. So in this case, I'll just go ahead and make that 0 and see how that changes my water cuts. And the water cuts is the first thing that I actually would like to try to match in this step of the workflow. And I would like to make sure that I'm at least trying to match the stabilized portion of the water cuts, which you see we've done to at least a little bit more extent right here. We still see that we're over predicting our GORs, so a very efficient way to reduce some gas mobility is to increase this NG exponent right here. And what that will go ahead and do for us is to just reduce this relative mobility, so this KRG KRO ratio right here, and will allow for less gas to flow, and that's a good thing for getting at least a better match. So what you see here is that we're starting to get a very decent fit on our GORs for these 2 relevant type curves. And we see that getting our water in place a little bit better, our associated OIPs are at least a little bit closer to what we had in our flow material balance. So if we go back to our flow material balance, we said that 550 is maybe the appropriate oil in place. Here you can see that maybe this portion of the data here is even a little bit higher, getting it up to around 600. Here our OIP that is the closest type curve here, is 618. They are very, very close and consistent. And with that, I'll say that I'm happy with my analysis in my numerical RTA. And the other thing, just before I do that, is that you see my LFP is also higher than my LFP from my analytical RTA, which also makes sense. I've checked out the constraints for consistency that I like to look for, and I'm ready to then go into the numerical model. And if I'd like to export these results into the numerical model, I just simply click export right here.